Hi everyone. In the last lecture, we have seen in detail that what are some of the important functions in reinforcement learning and what is meant by getting a return in reinforcement learning. We saw that the state value function is basically a function. Given a state, it tells us that how good is this state under this policy, under any policy by. And the same goes for action value function, that given a state and then an action that you took from that state, it tells us that how good was taking that action A under any policy by. So if you take the same action in the same state S but under a different policy pi of dash, the Q value for it is going to be different than this Q. So we have to remember that these state values and action values are always in correspondence to a certain policy. We saw their formulas that the expected return of a state S depends upon. So yeah, sorry. The it says that the return that you expect from a given state S is given by the state value function, and the return that you expect given a state A, thus given a state S and taken an action A, is given by the action value function. The symbol, this capital E like symbol, represent expected, not deterministic. It represents the expected reward, because we have this concept of exploration versus exploitation in reinforcement learning, which means that most of the time when we get a reward for an action, we try to repeat that action, but there is a possibility that we might want to try new actions as well. So basically, in order to further clarify the concept of exploration versus exploitation, if I get a reward, if I am in a state S and I know that this action A is going to give me the best reward possible that I know so far, which is 10. The next time I am going to reach this state S, I'm going to repeat this action A. But there is a 20% possibility that I might not choose this action A and instead choose an action A2, which might lead me to a different reward. Now, this different reward might be better than this 10 or might be less than this 10. We do not know. But this is the beauty of reinforcement learning. We try, we sometimes we exploit what we already know, and sometimes we explore new things so that we can get new information and then we can optimize. So if uh, let's say if I got a better reward than 10, if I got 15, then the next time I come to this state, I'm going to take this action A2 rather than the action A1. But if under exploitation, but if again I want to explore a new action, I might take a new action A3, and A3 might not give me a good reward. It might give me 2, which is the worst in all three of them. So then the next time I'm going to uh, come to this state as, I will always try to take this action as A2. But if there is an action A4 which I have not taken yet, with an action which I have not taken so far, there is a possibility that even though most of the times I take action A2, there is a possibility that there is going to be a time that I take the action A4 instead of action A2. So I hope I have been able to convey that most of the times we exploit the knowledge that we already have about the environment, but time to time we also explore that what if I do something that is not optimal according to my knowledge. There is a possibility that I might get even higher rewards compared to what I already know. So this is basically the notion of exploration versus exploitation. It is a huge topic in itself, but for right now we do not need to go into the details of it. Just remember that most of the times we exploit the network, but there is a chance that we might explore the network as well, because there is a possibility there are some actions that can give us even greater is rewards than what we already know. So now I'm going to start the famous Bellman equation. This Bellman equation is a very interesting equation because it can get as difficult as you want, it can get as confusing as you want. So the best thing you can do with respect to Bellman equation is that learn it only for the purpose you are learning reinforcement learning. We are learning reinforcement learning to understand reasoning in LLMs. So I am going to narrow down the derivation and the explanation of the Bellman equation so you do not get drowned into the complexity of the Bellman equation. If you want to drown into the complexity of the Bellman equation, I'm going to give a link of the video which is going to give you the complete mathematical detail of the Bellman equation, and you can happily drown in it. If you are someone like me, then you might drown in it unnecessarily without any need, but I do not recommend doing so if you are solely learning reinforcement learning for understanding reasoning LLMs. So yeah, too much off topic talk. Let's get back to the Bellman equation. I know the sound quality is pretty bad, but it is what it is. I will try to buy a better speaker next time, and we are going to understand Bellman equation. So the Bellman equation. So the Bellman equation is used to find the action value or state value given state or a state action pair. I repeat, the Bellman equation is used to find action value or state value. For example, I am in a certain state S and I want to find how good it is to be in this state, then what I'm going to use, I uh, am I going to use the action value function or I'm going to use the state value function. If you I want you to answer it before I answer. Obviously, we are going to use the state value function because state value function is a function which tells us how good it is to be in a certain state when we give it our state. Okay, it was a little bizarre, but yeah, basically, uh, the state value function is going to give us the value of a state, that how good it is to be in this state. So we pass the state into the state value function. Now on the right side, you see this thing. What is this thing? This is R, R, that old friend of ours. So basically what happens is that we are in a state A and we take an action, sorry, we are in state S and we take action A, and because we take an action we receive a reward R, and because we have taken an action we reach into a new state which is represented as S dash. So the Bellman equation for state value function dictates that the state value of a state is equal to the immediate reward you get plus gamma times the state value of the next state. What do you mean by that? I said that the Bellman equation states that the state values, the state action value of a state is given by the immediate reward R you got plus gamma times the state value, the state action value, sorry, not the state action value, the state value of the next state. So if I am in state S and I want to estimate that how good it is to be in this state S, I'm going to use the Bellman equation, and the Bellman equation dictates that the V of S is equal to R plus gamma times V of S dash. I want you and I've repeated it so many times to find a problematic symbol here. We are trying to find v of s, and in the equation of v of s we have the v of s dash, that is the next state. So does that means in order to find the v value of a state, we need to have the v value of its next state already with us? Yes, it looks like what it looks like. It looks like a circular dependency. So that means that when I'll be in state s dash, I would need to have the value of s double dash, which is the state I reached from s dash. So how does this whole equation gets calculated if there is a circular dependency? When I initially started learning reinforcement learning, I was totally flabbergasted by why are we having this circular dependency here. Well, the answer to that is that in reinforcement learning, everything is initialized randomly at first. Listen to my words. In reinforcement learning, everything is initialized randomly. Now, that randomly is not as random, and if you get into the nitty gritty details of reinforcement learning, there are 100 ways to initiate the values, but I'm going to stick with random values here. I'm saying that in reinforcement learning, we initiate the v values randomly. So there is going to be some random v value for this state s, and there is going to be some random value for this state s dash, and based on this random value we are going to calculate v of s. Initially when we have just started, obviously this v of s is going to be wrong. There is very less chances that it is going to be correct. Initially it is going to be wrong, but with the passage of time, with more and more experience, our estimation of v of s is going to get better and better. Eventually we will reach a point that v of s is not going to reach. So it might start from a value of 10, then it might get 9, then it might get 8, then it might get 7, but once it has reached 7 it will stop being less than 7, and at that time we will come to know that indeed 7 is the actual value of v of s. We started with a random value 10, but with playing the game more and more, playing the environment more and more, we have come to know that the actual value of v of s is 7 under what? Under this policy pi. So yeah, the Bellman equation gives us a formula to calculate the state value or the action value given state and action. The same methodology, the same mental model that we have implemented here can be used here as well. So don't be confused. This is the same thing. In order to find the action value given a state action pair, it is going to equate to the immediate reward you get after taking this action A plus gamma times the action value of the next state action pair. If you have forgotten this gamma is the same discount that we discussed before. Let me just confirm whether uh yeah, yeah. So this is how you use Bellman equation to find the action value or the state value given state action pair or just the action. Let's go back to the slides. um okay, in the next section we are going to understand what is meant by temporal difference error and how does the Bellman equation um, relates to it.